Section II.D introduces the idea of linear correlation and regression. So we've already talked about the idea of linear correlation graphically. In the last section, we introduced the idea of scatter plots, and we talked about identifying linear correlation as positive, negative, and then we talked about the situation where the correlation is perfect and all the points are exactly on a line. Of course, there is also nonlinear correlation. In this section, we will begin by focusing on the idea of how we actually measure both the strength and the direction of that linear correlation. Linear correlation, in terms of direction, it is very simple. We've already talked about the direction, really. The direction is simply, is the relationship positive or is the relationship negative? When we talk about the strength of a linear correlation, we're talking about basically how close are the points to the line. So that's why the perfect correlation scenario is an important thing to understand, because it is a good reference point, because the strongest relationship you can ever have is when all the points are exactly on a line. So we call that perfect linear correlation. Of course, when you collect data, you're never really going to get a perfect relationship. So what we want is we want values that are close to the line, and the closer the points are to the line, the stronger the relationship is. So when I talk about direction, I'm talking about, is it positive or negative? When I talk about strength, I'm talking about how close the points are to the line. So in order to measure the linear strength of a relationship between two variables, we will use what's called Pearson's product moment correlation coefficient. It's also called the R value, and that's what we'll typically call it. We'll typically call it our R value. So the R value is something that you can calculate from two quantitative variables. It will measure the linear strength between the two variables. The thing that we will not do in this class is I will not give you a set of data and ask you to calculate the R value. The formulas are given to you in the notes if you want to see them, but you will never have to use those formulas. So the way that we will get these R values is we will use StatCrunch. So when you do some of the assignments, you will use the software in order to calculate R. The other thing that sometimes will happen is, like on the homework, I might just tell you what the R value is, or I might give you output that identifies the R value. So one of the ways that you will see output is you will see a correlation matrix like you see on the slide here. A correlation matrix will allow you to look at correlations for lots of different variables. So you can put a bunch of different variables in a software package and it will give you a correlation matrix. And basically each cell of this table tells you the R value, or the correlation coefficient, for each pairwise set of variables. So that's what we're looking at here. Basically, each cell represents an R value. So let's talk a little bit about what R is, because the thing that you will have to do is you will have to interpret the R value. So it's important to know some general rules about what R looks like. So the first thing is, in terms of R, is because of the way the formula is set up, R will always be between -1 and 1. So you will never get an R value that is not between -1 and 1. R can be 1. If R is 1, well, let me start with the sign. So it's between -1 and 1. So the direction of the relationship, or whether the slope of the line would be positive or negative, is really simple to tell from the R value, because basically if the slope is positive, then the R value will be positive. If the slope is negative, then the R value will be negative. So it's really that simple. So to determine whether the relationship is positive or negative, all you have to do is look at the sign of the R value. If the sign's positive, like I said, that means you have a positive relationship. If the R is negative, that means you have a negative relationship. The value itself is what tells you the strength. So the strongest relationship you can have is at 1 or -1. So it's really the absolute value that tells you the strength. If you get an R value of 1, that tells you have a perfect positive linear correlation. So that's why that perfect relationship is an important idea, because it's the strongest relationship you can have. And like I said, perfect means all the points are exactly on a line. So if you get an R value of 1, that means perfect positive linear correlation. All the points are exactly on a line with a positive slope. If you get an R of -1, then that tells you that you have perfect negative linear correlation. So all the points are exactly on a line with a negative slope. So those are the kind of ideal values in terms of correlation. You would want to get -1 or 1. Of course, we're never really going to get those values. So instead, what we want is something close to that. What you don't want is 0. 0 will tell you there is no linear correlation. Actually, there could be another kind of correlation. Maybe some other function would fit the points well, but we're specifically measuring the linear relationship here. So it would tell you there is no linear relationship between those two variables. So you want something close to 1 or -1. You don't want something close to 0 is essentially what we're looking at here. So let me just give you some reference points that are important. I will say there is no perfect cutoff as to when we have a strong relationship and when we don't, but I am going to give you some general rules, and these are the rules that I would like you to use. So the general rule in order to be able to say that we have a strong relationship that we will use is as long as your R value is at least 0.75 in terms of absolute value, then that means we're going to have a strong relationship. So that's a good number to keep in mind. At least 0.75 in absolute value means that we have a strong relationship. It means that it's close enough to 1 for us to be able to say it's strong. Anything below 0.3, we will say there's no linear correlation because just like when you calculate an R value, you're never going to get -1 or 1. You're also never going to get exactly 0. So anything less than 0.3, close to 0, we're going to say there is no linear correlation. Anything else, anything in that 0.3 to 0.75 range, some people will break that into like weak and moderate, but we're just basically going to call anything between that 0.3 range and that 0.75 range. We'll just call that there is some relationship there, but it is a weak relationship. Okay, so let's start interpreting some values. So let's look at this correlation matrix. And the first thing that I'm going to ask you is, in this correlation matrix, what is the strongest correlation? So you're basically looking for the biggest value here, but you do have to be a little careful. One of the mistakes that people will make is they'll pay attention to the negatives and they won't consider the negatives in terms of their strength. So what really matters is not the sign. The sign only tells you the direction. So you're really looking at the absolute value here. And you'll see the biggest value in terms of absolute value here is that relationship between the weight. These are all vehicles, so it's the year of the vehicle, the highway miles per gallon for the vehicle, the weight of the vehicle, and the value of the vehicle. And you can see the highest absolute value here is that relationship between the weight of the vehicle and the highway miles per gallon for the vehicle. That relationship gives us an R value of -0.968. So that absolute value of 0.968 tells us that that is very close to 1, or really -1 in this case because the relationship is negative. That tells us that that is really close to -1, which means this is really close to being a perfect relationship. It's obviously not, but it is a very, very strong relationship that we have here. Definitely bigger than that 0.75 value. So that is the strongest correlation that we have. The sign of the correlation, I've really already said this, but it's important to think about what that really tells you in terms of the variables themselves. This relationship is negative. That does mean that the slope is negative. But think about what that means in terms of the variables. When you have a negative slope, what that means is that small values of one variable occur with large values of the other variable, and vice versa. So in this case, if you think about it, it makes sense, because if you think about cars that have a small value for weight, so cars that are very light, are going to have high miles per gallon. If you think about really big and heavy cars, they're going to have low miles per gallon. So big values of one variable occur with small values of the other variable. The values in the middle occur together, and that's why you get this negative relationship. That's what happens in a negative relationship. Of course, in a positive relationship, small values are going to occur with each other, and then big values are going to occur with each other. But this one is negative. As you increase the weight of a car, it only makes sense that the highway miles per gallon is going to decrease. So that's why we get that negative correlation. One of the things to always think about with this idea of correlation, and one of the mistakes that is commonly made, is you want to be careful to distinguish between correlation and cause and effect. Sometimes the reason for a correlation between two variables is that one variable is causing the other. But you have to keep in mind that that is only one of the reasons why you will end up with a correlation. There are other reasons why you might have a correlation. So the general rule to this question, I will ask this question multiple times in the class, is this question says, does this correlation allow us to say there is a cause and effect relationship? Anytime you're asked, does the correlation allow you to say causation? The answer to that is always no. Correlation by itself does not mean that it's a cause and effect relationship. Now, could it be a cause and effect relationship? It could. Correlation is one of the things that you would have to show in order to show cause and effect, but it is only one of the things. I'll give you my favorite example. My favorite example is if you look at, in the United States, if you look at ice cream consumption over the months of the year, and you correlate that with the number of assaults over the months of the year, you will find that those two things have a strong positive linear correlation. But I think that we can all agree that it's not the ice cream consumption that is causing the assaults. So it's not a cause and effect relationship. Even though the ice cream consumption is correlated with the number of assaults, it's not a cause and effect. It's something to be careful of because people love to jump to that conclusion that because they're correlated, it's cause and effect. So why is there this relationship? Well, this relationship is really driven by a third variable. It's driven by the weather outside. When is ice cream consumption the highest? Well, it's highest in the summer, and when it's nice outside, ice cream consumption is the highest. Not as many people love to eat ice cream whenever it's freezing outside. The high values tend to occur when the weather's nice. The low values occur to tend whenever it's cold and not as nice outside. If you think about assaults, actually assaults work the same way. Assaults are always highest in the summer and lowest in the winter. In the summer, there's more people out. There's more opportunity for bad things to happen, and there's more assaults in the summer than in the winter. So basically, if you compare those two variables, what happens is the high values occur at the same time, the low values occur at the same time, the values in the middle occur at the same time. So that relationship is a strong positive linear correlation, but it's not a cause and effect. What that is called that's called what we call a spurious effect. And a spurious effect is when I have some other variable, or it could be multiple variables, but we have something else causing this relationship basically other than cause and effect. So a spurious relationship is like I have temperature that's driving the relationship between ice cream consumption and number of assaults. So that's the idea that you got to be careful of. Is there some other reason why this correlation could occur other than cause and effect? So you always have to really think about that question. So let me just run through the things that you have to show in order to show cause and effect. So to truly show cause and effect, you have to actually show four things. You have to show that time order. So by time order, we mean the cause has to, of course, happen before the effect. So for it to be cause and effect, the cause must happen and then the effect. Otherwise, it doesn't make any sense. Number two is there does have to be what we call covariation, or basically correlation. There has to be a statistical correlation or relationship between the two variables in order for it to be cause and effect. If there's no relationship, then of course it's not cause and effect because there's not even a relationship. The third one is there should be some rationale as to why your variable X is causing your variable Y. So there should be some reasonable rationale as to why this is occurring. So those three, in lots of cases, are pretty straightforward to show. It's pretty straightforward lots of times to show the time order, covariation, and the rationale. The one that's tough is this idea of a spurious effect. How do we call this? We must show non-spuriousness, which means we must show that there is no spurious effect here. There's no other variable that's driving this relationship, for example. So technically what you have to show is you have to show that it is X and only X that is causing the changes in the dependent variable. To be technical, that's what you have to show. So you have to rule out any other explanation, and that's almost an impossible thing to do in many cases. So it's really, really hard to ever be able to show number 4 is true. So because of that, it's very hard statistically. You can never just statistically, based on statistics, you can never say cause and effect just based on the statistics. You have to be very careful about that. You need more than just statistics. Now, if you're talking about a case like maybe a medical case where we can say lung cancer or smoking causes lung cancer, we might be able to say that, but there's also medical reasons as to why we can say that, not just the statistical relationship. So we have medical reasons that allow us to say this is actually the cause. And because of that, we can satisfy this 4th characteristic of non-spuriousness. But in many, many cases, it's really difficult to rule out all of these other rival explanations. So in those cases, you got to be really careful not to jump to the conclusion of cause and effect. It's a common mistake that I see, is I see people love to jump to the cause and effect conclusion just based on correlational data. It's something to be really careful about. Let's just look at a few other correlations here and make sure we're on the same page about how we interpret those. So let's look at the correlation between the year and value of the car. So I'm going to round all these just to 3 decimals. If you look at year and value, you'll see that if we round, that's 0.786. So 0.786 does satisfy our criteria for being strong. Remember, at least 0.75 means we have a strong relationship, so that one barely meets that criteria, but it does meet it. So we're going to say it's a strong relationship. Notice that R value is also positive. So the way that we would interpret that is we would interpret that R value of 0.786 as a strong positive linear correlation. And this is really what you got to be able to do. You got to be able to look at these correlation values and interpret what they tell you in terms of the correlation. If we look at the correlation between highway miles per gallon, or year and highway miles per gallon, year and highway miles per gallon has a correlation of 0.491 if we round. So if we look at that value, it's obviously not strong. It doesn't meet that 0.75 criteria. It is bigger than 0.3, so there is some relationship there. And by the way, it kind of depends on kind of what kind of R values you tend to see. Really depends on the field that you're interested in. Like if you look at professional journals where they do research and they lots of times will report R values. Like if you look at the hard science journals like physics, chemistry, and those kind of hard science journals, you will pretty much only see really high R values. But it's because, like in physics, the outcomes that they deal with are very predictable. They deal with things that are very predictable based on other variables. So because of that, you tend to have very strong relationships. So you only get really high R values. They're not going to even report anything that's not a really high R value. But if you look more in the social sciences, you'll start to see R values that look more like 0.5 or sometimes as low as 0.4 or 0.3 maybe, because they tend to look at relationships of variables. So it's not that their research isn't as good, it's just that it's different because they tend to look at variables that are more that are really just less predictable. Like if you're looking at psychology or education or sociology, if you're like doing something where you're trying to predict a person's behavior, well, we all know how predictable human behavior is. It's just not very predictable. So we're looking at things, we can look at things that are related to human behavior and say that there is a correlation or a relationship there. But to get to that point of it being a strong where we're going to actually predict what someone's behavior is, we're just not going to be able to get there. So because of that, in those kind of areas, you tend to see a lot of these more kind of weak and moderate correlations where we can say these things are related. There is a relationship there, but it's not strong enough where I'm actually going to be able to predict someone's behavior. So whenever we're kind of in this middle range of like 0.3 to 0.75, we're just going to say there is a correlation. It's just a weak correlation. Some would argue maybe that there's a moderate correlation as you get above 0.5, but we're not going to worry so much about that. But here we get a R value of 0.491. That tells you there's a weak linear positive. I say linear twice there. So that's just a typo, no big deal. A weak positive linear correlation. What does the correlation for weight and value tell us? If we look at weight and value, you can see that that is 0.100. So since that is below 0.3, essentially there is no linear correlation there. Now technically there could be some other kind of relationship that's not linear, so you want to be careful. Don't just say there's no correlation. We're specifically measuring the linear relationship, so when you get something below 0.3, make sure you just say no linear correlation. So that's your typical interpretations. Pay attention to the sign. It tells you whether it's positive or negative. Of course, if there's no correlation, you don't have to worry about the sign. You just say there's no linear correlation. And then you determine whether or not it's strong or weak if there is a correlation along with the sign, and that will tell you how to interpret that value. So let's just look at some graphs. I just want to make sure that you have a feel for what things will look like graphically. So just some of the values that we've already looked at, let's just look at the graphs so you can see kind of what they look like. So this is the graph for the year and value of a car. This is called fitted line plot. And basically all it is nothing more than just a scatter plot. But we have a line fit to those points that follow the general relationship. And I'll talk about where that line comes from here in a few minutes. If you remember, the R value for this data set was 0.786. So we said this is a strong positive linear correlation. So that's how we identified this. So this is kind of where you're kind of getting close to that border of 0.75. So when you start getting down close to 0.75, this is what graphs start to look like. So you can see for the most part, most of those points follow that line pretty well. There are maybe 2 points that are starting to get kind of far away from the line. And that tends to be what happens when you start to get around 0.75, which is why we create our cutoff there. Is you'll find that most of the points tend to follow the line pretty well, but when you start to get down to about 0.75, you'll start to get a couple points that don't fit the line as well, and that's kind of why that's the cutoff. So this is your pretty typical graph where we're still going to say it's strong, but we are starting to get down close to that cutoff point where we're no longer going to say it's strong. So most of the points follow the line really well, but we start to have a couple points that are a little bit further from the line. So that's a pretty typical graph for around that 0.75 mark. This is the one for the value of the car and the weight of the car. Remember the R value here was 0.100 if we rounded. So here, this is where we said there's no linear correlation, and if you look at those points, you can see there really is no pattern here. So the computer is going to fit a line to it no matter what. But of course, you can see none of the only a couple of the points are very close to the line, really. Most of the points are not. There just is no real correlation here. So that's what it's going to look like when there's no correlation. The plots aren't going to be in any sort of pattern. Definitely not a linear pattern. This is what we really like to see. We really like to see graphs that look like this. This was the strongest correlation that we saw in the correlation matrix. This is the correlation between weight and highway miles per gallon. It had an R value of negative 0.968. Of course, do notice as compared to the last couple, this one here does have a negative relationship. So of course the R value is negative, and you'll notice in the graph, of course, the slope of this graph here is negative. So that negative slope is why we get a negative R, and that's always the way that works. Also notice here that all the points are really close to the line. So here we're getting close to -1. So we know that this is a very strong relationship. All the points are very close to the line, and that's why we love to see correlation coefficients close to 1 or -1, because that means we do have these really strong relationships. When you have these really strong relationships, or when you have anything above 0.75 will be the general rule, then what we're going to start to do is we can start to use the idea of regression, which is the other topic that we cover in this section. The idea of regression is now I'm going to fit this line to this data, and I'm actually going to use the line in order to predict a y value based on an x value. So let's talk through that a little bit. We're going to talk through that with this same scenario where we have this very strong relationship. Okay, so the goal in regression. The goal in regression is to predict. So most of the time we set up regression models so that we're basically predicting y, which is something hard to measure, based on x, which is something that is easier to measure. So we're going to predict y based on x. That's important to know. So since we're predicting y based on x, we don't have to worry about any error in terms of x, because x is something we're actually going to measure. So it could be something like we want to predict someone's reaction time based on their blood alcohol level. Blood alcohol level is what we're actually going to measure, but what we're actually interested in is their reaction time. So x, there shouldn't be any error to as long as we measure it correctly. So x, we're going to actually get an actual value for x, and then we're going to use it to predict y. So because of that, we say there's no error in x. We're going to measure it. But whenever we go to predict y, then we're going to end up with error in terms of y. So for example, if you look at the weight of the cars, there's a value out there at 5,000. So as you can see, there is a distance between the point and the line. So the distance in terms of x doesn't matter. So the horizontal distance there doesn't matter because we know what the weight of the car is. We weighed the car, it weighed 5,000 pounds. But what we also know is we know that this point is not exactly on the line. So that vertical distance from the point to the line, that vertical distance, that is basically my error. And that error is in terms of y. So whatever that y value might be, maybe the y value is 26 for the line, and maybe it's 27 for the point. So that distance between the point and the line, that's actually my error in this highway miles per gallon. So whenever we talk about that vertical distance between the point and the line, that is what we call our random error. So there is going to be some error if we use this line to predict these given outcomes, because all the points are not exactly on the line. So it's kind of like what you do in algebra, where you plug in x and you solve for y in a function. We know in algebra, though, for every x there's exactly one y, but in this case we're just using x to predict y, so there's some error there, and that error is that vertical distance between the point and the line. So let's talk about where the y comes from, because we have to understand the error before we can really talk about where the y comes from. So the whole goal of regression is to predict, which means whenever you pick this line, because the computer's going to do the line for us, you don't actually have to calculate the line yourself, but whenever we pick this line, we want to pick the line so that we get as good of predictions as possible. That's basically the goal. The goal is to get as good of predictions as possible when we plug in x to solve for y. So the way that we do this is we basically want to make the errors as small as possible, right? So in order to get the best line, we need to make sure that we minimize the errors. So notice all these points have a vertical distance between the point and the line, right? So every one of these points has a vertical distance between the point and the line. So we basically want to minimize those errors. So we end up with a similar problem as we do with variance, and I'll try not to get too mathematical on you here. But we basically end up with the same issue as with variance, only now we're in two-dimensional space, is like with variance. So we can't calculate average distance from the mean directly, because some of the points are below the mean, some of the points are above the mean, and if you subtract the mean from all of them and you add them up, you just get 0. So in the variance, what we do is we square those values, then we average them. So you end up with the same problem here. If some of the points are going to, if you draw any line through the balancing point of this graph, so the balancing point would actually be, there is a point on here that's the balancing point. So you can take the mean of all these x values. You can take the mean of all these y values. We would call the mean of the x's x bar. We would call the mean of the y's y bar. I wouldn't make you explain this to me. But there's a point on this graph that is the point x bar comma y bar. If we draw any line through that point, some of the points are going to be below the line and some of the points are going to be above the line. If we have a point below the line, then the error, we call those e values, that error is going to be negative. If we have a point above the line, those errors are going to be positive. If we add all those together, we're just going to get 0. So we can't just use the errors directly, because it has the same issue that we have lots of times in statistics because we use balancing point. We have the same issue of some are negative and some are positive. So what we end up doing is we square them all, and then we add those together, and we make sure that the sum of squared errors is as small as possible. So this method, you can see the question down there, the best fit line for the data is displayed in the graph above. The method used to determine this is what we call the method of least squares. So the method of least squares is what I just described. It's where you take all these e values, these vertical distances between the points in the line, all these errors, you square them, and then you add all those together. Whichever line gives us the smallest sum of squared e values, or sum of the squared vertical distances, that is our best fit line, because overall it gives us the least amount of error, which is the goal. That method is called the method of least squares. It is the most common method we use to pick a line, and for most people it's the only method you'll ever see, because you tend to not see other methods unless you really study a lot of statistics. It's called the method of least squares. So for our purposes, I will not make you really explain what the method of least squares is, but if I give you a definition or say, how did we pick the line, you should know it's the method of least squares that we use to determine the line. You should basically know that we are making the errors as small as possible, and why we do that. The way we do that is we just square them and sum them and figure out which one gives us the smallest total error. That's the basic idea. So I just want you to know the basic idea, not necessarily be able to explain the whole concept in a question. That's not the kinds of questions I will ask, but I want you to know the method is called the method of least squares. Okay, now that we established this line, then we can start thinking about using the line to predict. So let me just first talk about one of the issues that you have to be careful of with prediction. There are really two issues. One of the things that you have to be careful of with the line is extreme values. So if you have an extreme value in your data set, you should not use that line to predict. You should not say there's a strong correlation, because an extreme value can make a correlation look strong when it's not. This is the other issue. The other issue is the idea of regression is used for what we call interpolation. So it's used to predict within the range of your scatter plot. Extrapolation is the opposite of that, and we should not use regression to extrapolate. So this said, should you use the best fit line in the graph above to predict the highway miles per gallon for a vehicle that weighs 7,500 pounds? What would this be called? So the answer to that is no. This is called extrapolation. So notice if you look at your x-axis, the x-axis only goes from 2,000 to 5,000. So 7,500 is not within that interval. So it only goes from 2,000 to 5,000, which means we only know that this pattern holds between 2,000 and 5,000. We do not know what happens outside of that interval. So this pattern could likely change outside of that interval. So you should never predict for points beyond the range of your data, because we only know the pattern holds within our data set. We don't know what happens beyond that. So we can't assume that this pattern continues, and that this model or this line would work well to predict the miles per gallon if a vehicle weighed 7,500 pounds. So don't make that assumption. That's one of the mistakes that you will see with regression, is people will use it to extrapolate, which should not be done. Once you decide regression is useful, you decide you have a strong correlation. So that's always the first step, is to make sure you have a strong correlation, make sure there's no extreme values in your scatter plot. Those are the two big things. R is strong, no extremes in your scatter plot. If you have those two characteristics, then you can say, okay, now I can use regression and I can predict Y based on X. So this is a pretty typical regression output. Of course, the dependent variable here, that's your y variable, just like in the graph, that's your highway miles per gallon. The independent variable, that's your x variable, that is our weight. So the next thing that you'll see here is you will see the equation. So that equation, this is one of the main things that you're looking for, is this equation says highway miles per gallon, we can also just write that as y, equals 47.944282. So that's my y-intercept of the line, minus 0.0045219941. So that is your slope, times the weight, which is x. So that is your equation. If you want to predict y based on x, that's the equation you use. The sample size is 10. That's straightforward. There's 10 points in the graph. The R value, that's the same R value as you saw before. This is where you get it on this kind of output, is it'll just tell you what the correlation coefficient is. It's negative 0.968 if we round. The R-SQ, that's actually your R squared value. So if you just take that R value and you square it, you'll get R squared. R squared technically represents the percent of variation in your model, the percent of variation in Y explained by your model, or explained by X in a simple case. So that is basically a percentage. You will lots of times see R squared written as 94% if you round that, but it's nothing more in the linear case than just that R value squared. That last quantity, you don't even have to worry about that. That's just a measure of error. It's something that we won't discuss in this course. So let's use the regression output to predict the highway miles per gallon for a vehicle weighing 3,000 pounds. So the big thing there is if you're asked to predict, use the equation. So you can see this is the equation from the output. I did change highway miles per gallon. I just wrote that as y because that's my y variable. And I did change weight and I just wrote that as x. But that's nothing more than just that equation that the software gave us. So notice we don't actually have to come up with the equation. We just have to get the equation from the output, and then once we have the equation, then we can predict, and that's how this process is going to work. So to predict y based on an x value of 3,000, we do nothing more than just plug in 3,000 for x, and if you plug in 3,000 for x, then you will get a predicted value for y of 34.378 miles per gallon. So once you get the regression equation, it's simple. To predict y based on x, you just plug in for x and solve for y. That's all you have to do. The other thing that I'd just like to mention here is, would you expect a large amount of error in this prediction? And of course the answer to that is no. The reason being is, remember that we've already established that we have a strong relationship. The R value here is negative 0.968. So we have a very strong negative linear correlation here. If you have a strong relationship, then you would not expect a large amount of error in your estimate. You would expect some, because you don't expect to have a perfect relationship, but you would not expect a large amount of error. You would expect your error to be small. Now, if you get beyond having a strong relationship, then you're going to have a lot of error. And that's why we only use regression to predict when we have strong relationships. So once you determine that you have a strong relationship and you use it to predict, you expect to have some error, but you expect that error to be small. So that's what we cover in this section. Section 2D is a lot about just understanding the basics of correlation and regression. Understanding how to interpret that R value in terms of correlation is super important in the field of statistics. So make sure you understand how we're going to interpret that R value. And then with regression, once you get your regression equation, we're going to use software to get our R and our regression equation. Once you get your regression equation, you got to be able to use that regression equation to predict. And of course, you would only predict when we have already established that we have a strong relationship. So that's really the focus of this section. A lot of this is interpretation, and then just being able to predict based on that regression model, which is just a linear equation. So that's it for this section. That is the end of section 2D.